So next one is iDMA, tapping into near real-time data. And presenting for this session is Robin Corby, Commercial Sales Manager at Technolog, Daniel Woodworth, Network Strategy Manager, SCS Water, Tom Woolley, Business Development Director, RHD HV. So Daniel and the team are going to provide insights into delivering a company-wide intelligence network in AMP7 and how that is going to reduce leak runtime, increase operational efficiency, improve customer efficiency, and reduce environmental impact.
Okay, lovely, thank you. Okay, well, yeah, thank you for having us here to present.
Yes,
we're going to be talking to you about SCS Water's Intelligent Network project, which we're calling the iDMA project. So delighted to be joined today by two partners on this project. So Robin Corby from Technolog and Tom Woolley from Royal Haskell DHV. I think the fact that the three of us are speaking today really shows what a collaborative project this is and how we really see collaboration as helping to deliver this for us. Okay, so I thought I'd start just by introducing sort of some of the aims of the project, and hopefully you can test this as we go through the presentation. And I've got a case study at the end, and I'd like you to kind of think back to these aims to see if you feel we've met what we set out to do. So what we're trying to do here is get a reliable and consistent near real-time data from our network. And with that, we'll be getting real-time alerts with high confidence levels on those alerts so that we can act on them and make the best decisions. So it's all about putting our knowledge at the fingertips of our operational staff so they can react quickly, make the right decisions on site. And it's about having that information-backed decision-making. So not being put on the back foot, but rather being on the front foot for that. You know, we're looking at improved location and detection times. So you heard Jeremy Heath earlier talking about the palm analogy. So this is very much in the field of location and detection and reducing that part of the leakage life cycle. And if we can do that, we can reduce the runtime of the leak and the impact and the volume that it therefore has on our network, on our customers. And we want to improve our leakage position. Obviously, that's one of the main aims, but there are many other benefits as well. So this will have a positive impact on supply interruptions and on burst main performance as well as other performance commitments such as customer service measures as well. And that brings me on to the customer service element. So you know, really what we're aiming to do here is know about network events and issues before our customers do. Again, it comes back to that point about putting us on the front foot. We in our business, we often talk about the golden hour concept. And so, you know, if we can act in that golden hour, you have a lot more options than you do if you let things run on for longer. Approved information to update and advise the customers. So when things do go wrong, and sometimes they do, the customer will call in and want answers. If we've got the data to back us up, we can answer those questions much more easily and with the best information. And we want to reduce the impact through the runtime. So again, you know, we accept that occasionally the network will fail, but we want to minimize the disruption that's caused by that failure. And earlier identification. So, you know, the aim is to get there, solve the problem before the customer's even noticed. So as I've said, we aim to deliver this all through a collaborative approach, and that's working with our key partners on this project. So just to share with you what our vision for an intelligent network is, and this is a slide that I've been using for quite a while now, but I want to make the point that this isn't one size fits all. So what we found, even within our relatively modest stock of DMAs that we manage at SCS Water, you need a variety of sensors, a variety of different attributes that you're measuring, but you need a common way of getting that data and that information back, and then ideally a common method for processing that data and producing insights from it. And that's what we're aiming for here with our vision of an intelligent network. I call this a vision. It's not really a vision anymore. We're actually up and running now. We've got near real-time data coming in with it in all of our DMAs now. and we are on the cusp of having the AI engine running on that Tom will talk to you about, running in all of the DMAs as well. So this really is becoming a reality across the entirety of our network now. And we identified quite early on that there were building blocks and stages on this journey that we needed to go through. And this is, really where we decided that we needed to team up with the right people. So, we've got sensors, and Robin will speak to you in a minute about what Technolog bring to this project. You've got the communication piece. We're using the Vodafone NB-IoT network for that. And the processing layer is what Tom will speak to you about, the Royal Haskoning are bringing as well. So I'll pass over now to Robin, who's going to take you through the first of those building blocks.
Thanks very much, Daniel. And just similar to you, can I just check that everyone could hear me okay? Just a thumbs up. Okay, yeah, as Daniel mentioned, we want to
we can
provide near real-time data, and to do that we have to provide the two building blocks that you just showed you in terms of enhanced communication and enhanced sensors. And one of the ways of having that with the enhanced communication is enhanced technology in that field. And a key element around the characteristics of NB-IoT lends itself greatly to the characteristics of our loggers that have been deployed. To date, there's over 600 loggers deployed in SES Water with this technology. And I've given you a snapshot of where they are, and I don't expect anyone to go out in a Pokemon Go style looking for these loggers out there in the Sutton region. But there's a high density of logger deployment that's out there. And these are largely deployed underground, so the signal needs to be have the best opportunity for the data to be transmitted through the remote communications technology. And NB-IoT lends itself very well to that because it works on lower frequencies, lower bandwidth, and it gives that extra ability to penetrate the likes of lid covers or buildings to get to our devices, so it could reliably transmit that data as and when we need them. As I mentioned, also, it's quite a high density of deployment out there. So when you have the infrastructure, you want infrastructure that's available, and to reach a large range, a long range of where these loggers are deployed remotely. So when you have certain masts with the infrastructure in place and you have several loggers, this gives you a great opportunity in terms of getting the penetration and the distance of the signal as far to the end of your catchment. Similar to that, because I mentioned earlier, the low bandwidth that operates in NB-IoT enables the device to run at lower power requirements. So they allow the hardware, the cellular hardware, to run at a lower power than it did in the kind of 2G world. So that allows the device to last longer if it's using that particular technology. And it also lends itself to the type of communications that are typically transmitted, which are frequent communications with small packets, which I'm going to demonstrate here. We'll go on to the next slide. Thanks very much. So, what do you need for enhanced data? So it needs to be near real time. It has to be reliable and consistent, and to provide additional sensor metrics. There's some more information about your network. And we've have a long history of working with SES Water, and I wanted to show with this slide that we've got, in some cases, up to 10 years worth of data, reliable data. And traditionally, as you can see from the line in the graph, that's typically been flow and pressure data. So two channels of data that's been transmitted every hour, so 60 minutes. So we've got a lot of data that's available, but moving into the new world of the iDMA, you have to provide more information about your network and provide that consistently without having a detrimental effect in terms of the operation of the device and the length of time that it could, the life cycle of the asset within the ground. So as of the installation, we're able to move from having 2 channels of data to 8 channels. And I'm selling it short a little bit because one of those channels is a statistical channel, which provides the maximum, minimum, mean, and standard deviation of pressure, and will help with things that Scott Taylor was talking about in the previous presentation in terms of detecting PRB instability. So, and also providing other new metrics that are being looked at more in terms of temperature of not just the ambient temperature, so the environmental temperature, but the temperature of the network as well, and how that change in temperature manifests itself in terms of bursts and events within the network. And this data now is being transmitted every 15 minutes and has to work seamlessly with the AppSuite software to provide that data and as and when it needs it to run. So if we go on to the next slide, Daniel. So the key part of all of this, as we mentioned probably several times throughout the day and also within this presentation, is the collaboration, that element. So we need to work together to make sure that all parts can provide what they need to do. So one of the key priorities for me was to ensure that SES systems had the consistent data that they always had, and those links are maintained, but also add to their capabilities by adding additional channel data to the existing systems and the new systems that are being developed and implemented. So that means working with AppSuite and SES Water to come up with a consistent way of collecting that data and a consistent and robust way of transmitting that data to their systems and to the right systems on time. And all of these systems run pretty much like clockwork, so the data has to be there and available for them to do that. If that falls apart, then the next part cannot be maintained. So that's why I'd like to hand over to Tom so we could talk about how our data is being used with the AppSuite system.
Thanks, Robin. And just check everybody can hear me okay as well. Great, thank you.
Yes,
so
we can, yeah.
Robin and Daniel have really set the scene in terms of the data that we need for AppSuite. And key to what Robin mentioned in the previous slide is it's really important we get that data reliably and consistently and in a timely fashion. Because what we're trying to do is to provide, I suppose, two outputs for the project. The first one being detection of leaks. So we enable Daniel's team to be able to see when a leak has happened in real time. So we want to take that data in from the Cello data loggers provided by Robin and Technolog, analyze it, do the machine learning detection, and then tell Daniel's team whether he has a problem in his DMA and whether he needs to get his crews out there to look at that. And that all needs to happen really quickly. So just as Robin was saying, we need to get that data through every 15 minutes because our analysis doesn't just depend on the single instrument. We're looking at the whole DMA as a system. So we need to get the pressure data from the critical point, we need to get the flow data from the DMA, and use all that data together to detect any deviations and hence any leaks. What we're doing is importing that data from the sensors. We use our machine learning algorithms, which we've developed over the last 20 years, I would say, to predict what the pressure and flow should be at that particular moment. Now, I'm not sure how well the image is coming through for everybody else. It's a little bit blurred for me on the screen, but hopefully on that middle trend, the top trend there, you can see there is a blue line and a green line. And on the left-hand side, those lines are going along close together really, really nicely. And this is genuine data from one of the DMAs within SES Water. That's the predicted versus actual. So the green is the prediction, the red is the actual data. And then the blue line is the machine alert alarm limit. So what we're doing is we're looking to see that the red and the green are really close together. And if there is a deviation of the measured data away from the prediction, it then goes past that alarm limit and we raise a leak alarm for Daniel's team. And that's what you can hopefully see in the middle of that trend there. So the green and the red go along really nicely, and the red zooms up past the blue line and we raise an alarm. And that's the first part of the solution. So at that point there, as soon as that change has happened, in this case, because it's quite a big change, we raise the alarm and Daniel's team now know there is a leak occurring at that particular point. Most leaks don't tend to start appearing like this one here. So they tend to start with a smaller flow amount, and that might not be instantaneously visible as it would be in this trend here. So The one on the bottom, which I suspect isn't very clear for anybody, is actually looking at the effect of smaller deviations over longer time periods. Because a small leak, if you look at it in 1 minute or 15-minute samples, is very small. But if you look at that smaller leak volume over 1 hour, 2 hours, 3 hours, 4 hours, it becomes more apparent. And the AI is able to predict not only what's happening now, but also what's going to happen for the next hour, next day, next 72 hours. And all of that together can then start to pick up these small leaks, which eventually will become bigger leaks. So the idea is to get instantaneous awareness of any medium or larger leaks, but also pick up the small ones by looking at the effect over longer time periods. If you go to the next slide, Daniel, if you don't mind. The second part of the solution is helping Daniel's team to find leaks quicker. So the first thing is we've told the leak teams you've got a leak, and we can estimate the size of that leak as well, because the deviation away from the prediction of the measured data gives you an estimation of the leak flow. And that's fairly accurate usually. So we've got an estimation of the leak flow. What we then need is a DMA which has got multiple pressure sensors. So in the past, that would have been unrealistic because I think the technology wasn't available and it might have been cost prohibitive as well. But as we move to this era now where we've got IoT sensors, NB-IoT and other solutions, we can get to the point where you can have a DMA with maybe 4, 5, 6, 7, 8 pressure sensors within it. I mean, most DMAs already have 2. You'll have a DMA flow meter, which has got a pressure, and you'll have a critical point. So if you're looking at adding another 3 or 4 sensors, we can then use that leak flow estimate and that pressure data to locate where that leak might be. So the solution's got 2 benefits for Daniel. The first one is to tell him when a leak happens really quickly. So we're not waiting for a nightline analysis. We're just raising that as soon as it happens. And the second part is to enable his leak localization crews to go to a particular part of the DMA rather than look at the DMA in a whole. And obviously, in the age of leak crews becoming more and more scarce or more costly, being able to prioritize where they go to without saying go and look at the whole DMA, if we can just say go and look at that 20% or that 10%, then there's real benefits there in terms of efficiency, but also for the customer, because you can enable that leak to be found, repaired, and get people back on service much quicker as well. So we take the estimate of the leak flow. We then model the effect of that leak flow on the nodes throughout that DMA. So if you look at the DMA, and this one in particular, it's quite a small one, we model the effect of that leak flow on every node, and we calculate the likelihood of that node being the leak localization, sorry, the leak location point by comparison with the actual pressure data. So again, it comes back to the fact we need that data reliably because we're simulating, comparing simulator pressures with actual pressures in real time. And this all happens as and when the data comes through. That's why it's really key for us to get that 15-minute or even 30-minute data through reliably, consistently, and with really good date and timestamps. And we can then get to what we can see in the next slide, Daniel, if you don't mind. And this is the results when it comes up. It's quite a hefty image that might be difficult for people to see. This is the results of some actual tests we've done within a DMA, the first DMA in SCS water. So hopefully everyone can see towards the top of the page there's a gold star. So you can see the critical point. Hopefully just next to that there's a gold star. That was the location of the leak test. So there was a leak test performed there, which I think was around 1 litre a second. What we then did was set the burst find module going, looking for that leak. And the output of the burst find solution is likelihood of the node for being the leak location. And we represent that as colouring and size. So the bigger the dot and the darker the dot, the more likely it is for the leak location. In this case, you can see at the bottom left, you can see lots of small dots, green. At the top left, you can see lots of small dots, which are sort of amberish. But on the top right, you can see big red and black dots. And that shows that our solution detected that location as being where the leak is. So if this was a real leak, what would have happened is that burst alert would have detected the leak, burst find would have generated this simulation, and Daniel's crew would be able to look at this and say, right, it's really clear from this that we need to go and look for this leak at the top right-hand part of the DMA. And that's the big win. So we're not pinpointing the leak. I think that's challenging to do with pressure data alone. What we're doing is really shortening that time between the start of the leak and when the guys can get out there, pinpoint the leak and fix it. And if we go to the next slide, hopefully this image won't take quite as long to load. Here's a result of a second simulation, which is a similar size leak, which actually took place at the bottom of the screen there, the gold star. Hopefully you can see that. And we simulated this as well. So we've got, I think, only 7 pressure sensors in this DMA. We started the leak at that gold star. We ran burst find, and burst find quite clearly chose 3 nodes at the bottom of the screen as being the most likely location for the leak. So, and again, the actual leak was right in the middle of those other 2. So it gives a really good result. And the leak crew wouldn't need to go and look around that DMA. They could just go straight to that location. Additional techniques to then narrow it down to an exact point, and you can get out and fix it really quickly. And on the next slide, Daniel's going to talk through an example of how that might happen.
Okay, yeah, thank you, Tom. So, conscious of time, but I just want to quickly show you how this works and the benefits that you would get from it. So this is a real example. This is a burst that we had on our system, and I'm going to do a bit of a before and after. We had the advantage of this being in one of the test areas that we set up. So we had the opportunity to kind of look at what would we if we'd have been running live with AquaSuite when we had this burst. So you can see, and I'll try and point to it here. So we had the outbreak of the leak. This leak, it wasn't visible. So the first we were made aware of it was the day after. It's when a customer called in with low pressure. And we did send, it was at the weekend, it was on a Sunday. So we did send one of our out of hours crew out to look for it, but it wasn't visible. And this is a long rural DMA. We've got mains running across fields, and they didn't have much luck. They weren't able to find that leak until I think it was, well, yeah, early on the Tuesday, when the leakage team went back for a second try and managed to locate the leak. And that's when the job was raised. There were then some engineering difficulties. The leak was in the middle of a field. And so it took a fair few days for that to actually be repaired. We had to get the landowner permission, etc. So the total runtime of that leak was 77 hours, 3 days, and we lost 1.9 megalitres of water as a result. But if we'd have had AquaSuite working and we'd have been using it as an operational tool, it was working. We were just it was just in shadow mode. Here's what we could have done. So we had the AquaSuite alarm come through, and that's just the screenshot there of what it looks like and the email that gets sent to the operative to act on. So here's what the graph could have looked like, and try to bear in mind what we're trying to do here is squeeze down the detection and location time. So these sections here. So you know, this is based on some assumptions, I will admit, but I think they're all reasonable. So the leak would have broken out at 14:30, the same time. The alert would have come in and would have been by 1800. We would have had that alert. We would have immediately dispatched an inspector to the area who would have had access to the burst find, which would have pinpointed or located that leak to the section of main that it was on. We then would have found it a lot quicker, and we would have raised the job around about midnight on that first day. I've left the repair time the same because, as I said, there were engineering difficulties in getting in there. But what you can see here is that by dramatically reducing the detection and location time, you can really bring down the volume of water that's lost. And because we know leaks increase over time, it's that golden hour thing of really getting in at the beginning of a leakage outbreak, and that's where you get all the benefits. We also wouldn't have had the customer contact on this one as well, so there's other benefits there as well. Or if we did have the customer contact, we could have told them that we knew about the leak and we were onto it and there was a repair raised. So hopefully that just gives you a bit of an idea of what we're trying to achieve. And that's it from us. Thank you.
Great, thank you, all of you. We have a couple of questions here, which again, keeping an eye on time, if you could keep the answers fairly short. First one from Mikael Wilmot. Really interesting and very exciting presentation. Sometimes demand can appear as leakage, when using live data? Does this make false positives more likely? And if so,
thanks,
how
Michael.
can this be
Really
reduced?
good question. On the first slide that I showed, we've got the predicted versus actual in terms of prediction and measured data. We also have that machine learned alarm limit, and that's the key to filtering out demand and trying to prevent natural or normal demand being picked up as leakage. If your alarm limit takes into account how much that prediction normally varies from the measured data, because maybe your DMA is influenced by commercial usage, things like that, you'll naturally find that the band between the predicted and the alarm limit is a little bit bigger than what we saw in the image to start with. And in that case, you try and prevent normal demand being picked up as leaks. It's always going to happen, false positives, but I think we've done a lot of work to try and filter those out wherever possible. And we did develop this solution with 6 water utilities in the Netherlands, so we've got a lot of understanding of how to try and do that. But there's no simple solution, unfortunately, to say we'll never pick up a false positive, but we'll do our very best to prevent that.
Yeah, just to add to that, there is also some capability within the software to effectively link DMAs to each other. So this is to overcome, the sort of summer watering scenario whereby you know that neighbouring DMAs are going to react the same. And so if you see the behaviour happening in more than one DMA, the software is intelligent enough to alert you to that, or at least make you aware of it, and then not alarm on it.
Yeah.
One thing sorry.
Okay, we have two more questions. If I can just quickly ask them, and again, some quick responses would be appreciated. Adam Smith asks, can you please elaborate on the advantage of using pressure sensors in addition to acoustic loggers?
Thanks, Adam. The point I made at the beginning was that this isn't one size fits all, and so there most definitely is a place for acoustic noise loggers as well. I think we've decided to have a look at pressure as a means of localization, but we know that there'll be some DMAs where acoustic works well as well. I mean, one of the things we'd like to do is continue this project and look at actually getting some of the acoustic data to build into the software as well, and almost act as a validation potentially, or get pressure acting as a validation for it. So get them working together, because it's just going to add to the certainty of where you're ultimately going to go and look for the leak and dig.
Great. And the last question is from David Jacobs. Have you tested if the solution is capable of picking up smaller leak volumes that are typically found on supply pipe leaks?
Tom, do you want to take this one?
Yeah, go on. So yeah, I was about to say to David, the bit of supply pipe leaks are challenging for everybody. I think it depends on the flow in the DMA itself. So if your night line or your DMA flow is quite low, a supply pipe leak, not at an instantaneous point, so you won't pick it up on a 1 minute or 15-minute value. But if you look to the effect of that supply pipe over 15 minutes, over 4 hours or 12 hours, then yes, it might be possible. But it really does depend on what your background leakage is in the DMA.
Very good. Okay, we're going to have to close with that. Thank you very much, Daniel, Tom, and Robin. That's been a fascinating discussion.